Greetings. This is Graham Warren working with you on the coffee cart case. This is Graham Warren working with you on the coffee cart case. We're dealing with a coffee cart that is staffed by two baristas that serves two types of caffeinated beverage, espressos and lattes. And all we're really given are the various parameters of the inter-arrival time distributions and service time distributions. So let's have a look at espresso customers. They arrive at the rate of 3 per minute. That's a 20-second inter-arrival time on average. We've also got a standard deviation of 16 seconds. And so that allows us to calculate our squared coefficient of variation. So just recall what this squared coefficient of variation is. It's going to be the variance of the inter-arrival time distribution divided by the mean inter-arrival time squared, mean of their inter-arrivals. Okay, so, and the same is true for C sub S. It's the variance divided by the square of the mean. Okay, so let me just get rid of that. All right, so yeah, on the service time distribution, much the same. We don't have the distribution, but we're told that the service time is 10 seconds on average, standard deviation of 5. So very fast turnaround on that type of beverage. Latte customers take 50 seconds on average, 20 seconds of variation. And they're arriving 1 per minute. So 3/4 of your traffic is espresso customers, a quarter is latte customers, and quite different service time characteristics on these two types of customers. All right, so we have queuing analysis on this performed using approximations due to Ward Witt in his queuing network analyzer, and then also using Kingman's formula, which in itself is a heuristic. So sort of an estimate of what the waiting time on average is for both types of customers. It is 13 seconds. All right, so they are going to compete for the barista. So you really can think about this, the proxy customer here. Although the espresso customers get faster service, they are, in the same line as the latte customers, because we're pulling the servers. We're not having dedicating the baristas, having one dedicated barista for the espresso folks and one for the latte customers. All right, so let's have a look at the AnyLogic model. So I'm going to just lay out what we've got for the espresso customers here, and then the latte customers are essentially the same logic structure, but with different parameters, obviously, right? Inter-arrival time distributions, the inter-arrival time distribution for the latte customers and their service time distribution differs from that of the espresso customers. So the espresso customers again, I'm just going to go through some of the details here just so you can see what's going on. We're going to use what we call a truncated normal distribution. It has a mean of 20 and a standard deviation of 16. So what is this truncated distribution idea? So let's sketch this guy up. We're assuming that these times are normal, which is a leap. You have to make some kind of assumption to get this to go in AnyLogic. I mean, there has to be some concrete, explicit distribution. We're going to just say that we hope that it's roughly normal. We don't have better information. And you can go and collect more information and verify whether that is a reasonable model. But until shown otherwise, I guess this is a good starting model. All right, so the mean is 20, and then the standard deviation is 16. Now the problem here is that 0 is somewhere down here, and there is no matter what, some tail to the left of 0, and those would be negative times. Like if I go and sample from this distribution, I'm going to get a negative time. So we're going to use this part of the distribution declaration to make it a truncated normal. So what it does is it just essentially says, you know what, that stuff there doesn't exist. If you did sample from this distribution and you got a negative number, what's going to happen is the computer's going to come back and then resample, so you don't get a negative number. It's going to be none. It's going to be 0 or above. Okay. So that same idea is going to be used for the inter-arrival distribution for both types of customer, and same for the service time distributions for both types of customers. All right, so let's go and have a look at the rest of the logic here. All right, so on the service time distribution, which this is where the services occur, we've got exactly the same, but just with a different parameterization here, 10 and 5. Okay, so we're going to just walk through the logic here. So folks are generated. We start a timer on them because we want to figure time in system. We see the barista. Now the barista is a resource pool, and there are two of them. Right there's the capacity, and then once you've got a barista, the coffee gets made. That's this espresso prep feature here. And the time on that is 10, a mean of 10, standard deviation of 5, and again using a truncated normal idea to prevent negative service times. And then we release the barista, and then the barista can go and start on a new customer, and then we end the timer on that particular customer that we're considering, and then we just sync that customer, meaning just essentially gets destroyed in the simulation. But they're continually new customers being continually generated here. So same logic for latte customers, just different inter-arrival and service time parameters. And then with respect to the KPIs, we're going to use a statistics block here to capture using the .size function, which is a built-in function, capture the average queue length of the seed barista one waiting line. And so they actually, in the model, they're waiting behind other folks looking for especially customers, but they get served so as if they're in one, because the baristas are cool. So you have to wait for a barista, and then you finally get service. So same idea for the queue length for the latte customers, and we've got a utilization with a built-in. It's a .utilization function here. We're going to figure out what fraction of the time the baristas are busy, and then the final statistics we're going to capture are the distributions for the PDFs of the probability distribution functions of the waiting time in system for latte espresso customers and latte customers. And we're also going to get a mean off of that. Okay, so the model seems to be like two streams of customers that are independent and disconnected, but in fact they are connected because they both get served by this common barista resource pool. Now let's run this, and you're going to have to run this 3 times, but let's just see what the run looks like, and just at least get a feel for what the output's going to be here. So it's running slowly at this point. I'm going to just set this up so we can tolerate 50,000 instances or customers flow units being generated in these 3 versions of the AnyLogic software. Now, 3/4 of the customers are espresso customers, 1/4 latte customers, and so what I'm getting per minute is actually 4 customers. So if I were to simulate this thing for 12,500 minutes, that is 50,000 divided by 4, I will reach that 50,000 limit. So I'm going to go ahead and just set this up so that I don't exceed that, excuse me. So I'm going to just make it 12,499 just to make sure we're not, well, let's make it 400. How's that? So, and then hit enter so that 12,400 appears up there. Now it is running. You can see we've done 3 espresso customers, and we haven't had a latte arrival yet. So let's crank it up a little bit and wait for our first latte customer. Oh, there's the first latte customer. And you can see the queue length here is about 0.13. Down here, it's still 0. They're about 29% busy. And the average waiting time for the espresso customers, 10.5 seconds. And for latte customers, 52 seconds. But remember, they're only a quarter of the game. So if you had to figure out an average, it's probably something in the ballpark of 15 to 20 seconds, because 3/4 of the customers are experiencing this wait time. Right, so let's crank it right up and start to get some better estimates here. 13, 14 seconds, 54 seconds, 50% utilized, 55, going up. And I'll just run it all the way to completion now. All right, and there's your first run. And the queue length is about 0.3 customers on average. Oh, it's a very short line, 0.18 here. And the wait times, seems like for the latte folks, they're going to stick around for a minute total, even getting their service. But remember, their service takes 50 seconds. So the waiting time in the line is very, very short. And these guys get 10 seconds of service, so they're only waiting in the line for about 7 seconds on average before they get their, the barista start on their beverage. And these folks are busy 2/3 of the time. Okay, so to run another iteration to get better estimates so you can get confidence intervals going, what you need to do is to go to simulation main, and then just get yourself another seed. So I'm going to just change this to, for example, 1, and I can rerun it. And then it should, give you another iterate, and you're going to probably need to do 3 or more, depending on how variable this thing is, to get decent estimates. I'm going to again just set this up to go to 12,500. You really want to be consistent on something like this so that all your runs are created equal to the best of your ability, and we just run it to completion. So yeah, 15 seconds waiting time system for special customers, 58 here, and then maybe do a third one or fourth, fifth. Average those out, get your confidence intervals going. Okay, so this differs a little bit from, I think it was 13 seconds average that we got off of the queuing, but again, that was an approximation. This is an approximation because of the normal distribution assumptions on interarrival times and service times, but you've got to do this somehow. And this, the results seem very encouraging from a customer satisfaction perspective. Very short wait times in the line before they start on their beverages. So I think we're good. Hope you enjoyed this one.